Good day, everyone. Let's talk about the derivative of the function as its relation to the slope of a tangent line. So, by the way, what is a tangent line? You have your knowledge about the tangent line in your class in geometry in your junior high school. Now, let's use that knowledge to understand the derivative of a function. Now for the tangent line to the graph of a function at a point. So consider this graph of a function at a point C, and if of C, we can draw the tangent line to the curve as we would like to a circle. So you can create or draw an imaginary circle under your graph at a certain point, and then you can draw the tangent line on a point. You can see on this graph that among all the lines through a point C and FC, the one which best approximates the curve y is equal to the f of x near the point of C of f of C is the tangent line to the curve at that point. So these are just um, lines that intersect at point CFC, but the tangent line is this one. Okay, let's establish the tangent line on a graph. Let C be the graph of a continuous function y is equal to f of x, and let P the point on the graph C. A second line to the function through the point P is any line connecting from point P to another point Q. Let's label it as point Q on a graph. This is a second line. So at first, we have choose a point Q on the other side, at the right side of the point P, and then we will connect these 2 points. From point P to point Q, we created a second line, line PQ. Now we also choose another point, and we will label it as point Q sub 1 in between the point P and point Q. We will connect this one once again, and we will establish another second line, which is line PQ sub 1. And then another line here in between point P and point Q sub 1. We label it as um, point Q sub 2. So another second line that we could create, or a line PQ sub 2. So now we can see a sequence of second lines. If the sequence of second lines to the graph of the graph of y is equal to f of x through the point P approaches one limiting position, and that is the consideration of points Q to the left and from the right of P, then we define this line to be the tangent line, which is this one. So it means that we created a line that that connects point P to another point which is on itself at point P, and we label it Q. So that line is what we call a tangent line. So here's a formal definition of the tangent line. Let C be the graph of a continuous function y is equal to f of x, and let P be on a point on that C. A second line to y is equal to f of x through P is any line connecting from point P and another point Q on a graph. That are second lines. However, we call it the tangent line to the function at P. It is a limiting position of all second lines on line PQ as a Q, then it is also the same with its point. So Q, then P. The point P is the point Q as well. So that line is a tangent line. You notice that we use the articles a and the. So it means, when we say a second line, it means that there are so many possible lines that could attach from point P to point Q. But when we say the tangent line, it means a unique line. It is a one line only at that particular point. So it should be emphasized that if a tangent line exists, then it must be unique, much the same as in our limits. Before we could go on further, let's take to understand that there are some instances where the curve do not have a tangent line. So it's possible that the tangent line to a graph of a function at a point P does not exist. And there are two cases for that. First one is the case when the function is not continuous at x sub 0. So there are instances where a function is discontinuous at a point. It's because the limit does not exist, or the f of c is undefined, or the f of c is not equal to the limit of the function. In that case, that point do not have a tangent line. Okay, the second one is when the case when the function has a sharp corner or cusp at P. So it produces different limiting positions of the second lines of line PQ. It depends whether Q is the left or the right of P. So these are the example of curves that didn't have a tangent line. Example, the sharp corner at point P. So you can see if we evaluate it, at the left side this is the tangent line, while at the right side the tangent line is this one. So there are two different limiting position of a tangent line from left and to the right. Therefore, we do not have a tangent line. Again, a tangent line is unique at certain point, but if in this case there are two different and limiting position of a tangent or the tangent line. The second one is the cusp at point P. So essentially it's like the same of a sharp corner, but a cusp is it was formed when there are two curves that meet at certain point. Example, this one, there are curves that point that meet at point P. So it also created two different limiting position of tangent lines from the left or on the right side. So again, there are two cases where the tangent line doesn't exist. First, if the function is not continuous at a point, and the second one, if it has a sharp corner or cusp at point P. Okay, let's talk about the slope of a line. A line L passing through distinct points x sub 0, y sub 0, and xy has a slope of m of L is equal to y minus y sub 0 over x minus x sub 0. So this is the slope of a line. In your junior high school, we call it the slope is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 0. It's the same case here. It's just like we have a different label. Okay, for an example, we'll given a point A, 1 and negative 3, point B, 3 and negative 2, and C, negative 1, 0. What are the slopes of the lines line AB, line AC, and line BC? Okay, for number 1, the slope of line AB. So the slope formula, okay, L is equal to y minus y sub 0 over x minus x sub 0. So we will take the points of, okay, we'll just take the coordinates of A and B. For A, line A, that's 1, the x sub 0 and the y sub 0, while DB is the y and the x. Okay, so negative 2 minus negative 3 over 3 minus 1, that's 1/2. You can take the points interchangeable, but we could derive the same result.